Hey, so welcome back on the most easiest briefing of them all, the basics of the microscope. And it's literally going to be how the parts of a microscope, how to operate the microscope, and what a microscope actually does. It's really easy. So image quality of any microscope depends on two important properties. Those properties are resolving power and magnification. So let's look at that. The resolving power is the ability to distinguish between two structures that are close together. So a common example is when you do this with your finger, just one finger, and you stare at it, you can no longer notice the computer or anything else on the side, but when they're farther apart, you can actually see both of them. So it's the resolving power, the ability to distinguish between two structures that are really close together and stare at only one point. So microscopes with low resolving powers, they produce blurry images. Now we also have magnification. So magnification is the increase in the apparent size of the object. For example, this is what I look like right now. This is an increase in magnification. This is a decrease in magnification all the way back. So those are the two aspects of any microscope, resolving power and magnification. Now, in order to calculate magnification, there's actually a set way to do it. The ocular lens, or the eyepiece, which is the lens closest to your eye at the top, that usually tends to be a 10 times magnification. That's the standard setting. Then the revolving nose piece has three objective lenses. There's one lens here, there'd be another one here, and the other one on the side. There's three different levels of magnification for those lenses. The low power has a 4 times magnification, medium power has a 10 times, and the high power has a 40 times magnification. So you can choose essentially what level of magnification you want to see on your object. Now, the total magnification of any microscope is the ocular lens, the ocular magnification, multiplied by the objective magnification. Now let's make this hella simple. This is exactly what it would be like. You've got your eyepiece. It's going to be 10 all the time. Most of the time. It depends on if you're using a ghetto microscope or not. And then you've got your nose pieces. 10 times 4, if you're using the low power, that's 40. So your total magnification is 40. 10 times 10, if you're using the medium power, is 100. So your total magnification is 100. 10 times 40, if you're using the high power, which is 400. So your total magnification there is 400. It's super simple. Magnification is the this lens, which is the ocular lens, multiplied by the objective lens. Now, field of view is the area that can be seen through the microscope at any given time. So when you see through the microscope, you see a little circle. That circular area, the total area that you can see in that circle, that's your field of view. Now, it's actually calculated in a very specific way. Now, this shows that the low power field of view is 40, the medium power is 100, and the high is 400. This is how they actually compare to each other. That's the low power, and then the medium power actually manages to zoom itself in, and the high power goes all the way in. So low field of view is always the largest, then it goes to medium, and then it goes to high. So that's how they stack up against each other. Now, you can actually calculate the size of an object that you see inside the microscope using the field of view. Here's how we can do it. So we observe the ruler that we obtain under low power, and we have to actually get the diameter of the field of view. So we record within that circle, what's the diameter that we can see. Write that down. Then we count the number of increments, and we compare the object with the field of view to determine its size. Now, I'll give you a really good example so you can understand. 4 times 10 equals 40. So we have this field of view that we can see right here. This circle is the objective ocular lens, and that's the objective lens. So 40 times magnification, we see that it has a diameter of 4.5 millimeters. So 4.5 millimeters is the field of view at 40 times magnification. We write that down. So we're already done steps 1 and step 2. Now we go on to count the number of increments. So how many times this little cell type object can fit. So it'll actually fit, one field of view is 4.5, and the cell will fit 3 times, because one cell can fit here, one cell can fit here, one cell can fit here. So because we know that the cell will fit 3 times, it's 1/3 of the field of view, which is 1.5. So the size of the cell is simply 1 divided by 3, because that's the fit number, how many times it fits, so 1, 2, and 3, multiplied by the field of view. So that calculation would actually be like around 4, whatever. Uh, so under high magnification, you can't use the previous procedure that we just said with the low power counting the number of increments. There's actually another formula that we can use to convert. I'll show you how. High power field of view, so just remember high, low, low, high, and field of view and magnification. So here's how we can actually use this formula. Under high power field of view and low power field of view, that'll be equivalent to the low power magnification divided by the high power magnification. Now let's use it. So what's the field of view of that same object at 40 times magnification? Well, we use this formula, and we know that we wanted to find the field of view at high magnification, which is 40, and we had the field of view at low magnification, which is 4.5, and 40 times 400. Now we actually do the math, and we'll get x equals 0.45. How did we get this? You divide these two, 40 and 400, and you multiply by 4.5. Let me just confirm that. So yeah, the 0.45 millimeters is the magnification at high power, which makes sense because your field of view tends to decrease, remember? So at high power field of view, it'll be smaller than what it was at low power, which was 4.5. Now, we can actually make scientific drawings of images that we view from microscopes, and here's how we can actually calculate the scale. So you determine the diagram size of the object on your diagram, which you have drawn, and you divide that by the actual size, and that's equivalent to 1 millimeters divided by blank millimeters. Now, I will show you an example of that later. So now let's get on to the really easy part, which is the microscope basics. How do we take care of a microscope and all that crap that nobody really cares about, but the teachers force you to know it. Handling a microscope. So determine if your microscope is properly stored, nobody cares. You take out the protective cover, no one's an idiot. Check to see if the cord is wrapped around the bottom of the arm, okay? 4 times the objective lens is in place, so it's aiming at the 4 times, and the barrel was lowered to lowest level possible, so the diaphragm is at the lowest. And every time you turn it should look like this. When carrying a microscope, you carry it from the actual neck of the microscope, the edge. You just have to put one hand there. You can use your other hand to slap people. I don't really care. Blah blah blah. Focusing. Okay, this is how you focus. You first start off at 4 times magnification, so that's the lowest, and you use the coarse adjustment knob and the fine adjustment knob to make sure you can see it very clearly. Then you move on to the slide. I just said all that. Then you switch to the medium power, and you do the same thing. Focus using the fine adjustment knob to make sure you can see it really, really clearly. So now use and only use the fine adjustment knob. So the first time you actually use the coarse focus knob, and then the next time you use the fine adjustment knob. And now the last one, you don't want to smash the lens into the slide stage by focusing with the coarse knob at this point. Yeah, no one's stupid. And you switch to the high power and you refocus using the fine adjustment knob. Now, depth of field, it refers to the thickness of the plane of focus. So a plane is just a single level, and how thick that single level of the cell or whatever you're observing is. That's the depth of field. Your depth of field, the smaller it is, the more accurate you can see the image that you're trying to observe. Like, that's a very deep field right there. With the large depth of field, all the threads are in focus at the same time. So when the depth of field is larger, we can actually observe the things much more clearly. And with a narrow depth of field, less threads are focused at once. You must focus downward to view the lower ones and vice versa. So when we're using depth of field, just remember that the narrow depth of field The less threads are in focus, the higher depth of field, the more threads are in focus. That's simple. Now here's the last section on making a wet mount slide. So a wet mount slide is a slide that you can stick into the microscope that's actually wet. Some specimens can easily be visualized by placing it directly under a microscope, which is a dry mount slide. So sometimes you don't actually have to make the substance wet in order to see it clearly, so you just stick the substance into a slide and put it in. But some specimens are better when there's a drop of water placed on the slide. So it's a wet mount slide. And just once again, stick it in. Why is that? Because that allows the light to refract more easily, so you can see it much more clearly. And it also helps support the specimen. It fills the space in between the cover slips on the side, allowing light to go through in a tight space. We don't want to watch the video because no one really cares. And that's what it looks like. So you place your specimen, whatever you're observing, in there. You put some water in there. So now you have the wet mount side, and you cover it up. And then there you go. You don't have to use 2 drops of water. 1 drop will work if you're using fine. But if you're using a stain, then remember to use only 1 drop of water. No one cares about the 45-degree angle. Just gently drop the blah blah blah. Literally do this. Take the specimen you're testing, put it on the slide, put 1 drop of water, and cover it. There you go. It's that simple. If you've got bubbles, then gently tap the cover slip. Yeah. Blah 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 blah. Everyone knows that. So those are the basics of using a microscope. Peace out.